everyone. My name's Kurt Hardee.
And I'm Elizabeth Ruetschle, and today we're presenting on our project that deals with distributed ray tracing of large scenes using actors. So, to give you a bit of an introduction to our project, I want to describe what ray tracing is, which it's a rendering technique used to display light and the amount of light that is should be shown. So each pixel is traced to determine that amount of light. We wanted to use the Akka library for Scala because Akka is based around actors and messages. So actors can send messages to each other very easily across a network, and it's easy to divide up geometries and later distribute it across, especially if you have a large amount of data. And Akka's dynamic scheduling for messages limits bottlenecking, so there aren't a bunch of messages trying to get through all at once, and it kind of splits it up a little bit. So our project also used n-body simulations because our project had a large number of data points. Our approach was had 8 million particles to begin with, so we wanted to know we don't necessarily know exactly how many bodies there will be, and it treats everything as a particle or series of particles independent of everything else.
Now, our approach in general was to split it, the monolithic ray tracing methodology, into two main sections, a back end and a front end. And the goal of this was to provide a basis that we could later actually distribute data across. The back end should contain all of the geometry or all of the data that we actually want to ray trace. We want it to be as multi-threaded as it can possibly be. We want to, like I said, potentially distribute the data with Akka remoting or clustering across a cluster or across several machines. While the front end, on the other hand, contains the actual ray tracer, or the thing sending out rays, and it must be multi-threaded. But, despite being multi-threaded and concurrent, it doesn't need to be distributed. You can have this portion of it be completely monolithic and not split up at all, and that's totally fine. In addition, we wanted to use Akka and Scala as the main methodologies for this due to the fact that it's incredibly simple to use and intuitive to expand, while at the same time preventing a lot of things like race conditions from potentially being problems in multi-threaded or parallel environments.
So we started off with an embarrassingly parallel version, and this sends one ray per pixel. There's no interference between rays, and it sends the ray. If there's a hit, it sends that light back. So it's completely asynchronous. It comes back at any point. There's no method to the pixel showing up, and it only works if each processing unit has access to the entire geometry, which can cause bottlenecking problems, especially if the geometry gets very, very large and there need to be messages sent across. But Akka can help with that.
So we then wanted to actually break it apart, as we said, with the approach. And so the first step in that is to actually, in Akka and Scala, implement that simple, embarrassingly parallel version. To that end, we called it the cast ray function, and it assumes that you have complete access to every piece of data at all times. That's super simple and super identical to the embarrassingly parallel version, and as a result, it's also completely insufficient for any amount of distributed data at all. So, the next goal was to split it actually into two sections, which mirror the front end and back end sections that I referred to earlier. The front end version became the image drawer, which the image drawer actually manages the image and the input output necessary for that, drawing any colors that we tell it to the screen. On the other hand, we have underneath that the pixel handlers, one for each pixel, and each of those sends a ray or potentially multiple rays to geometry. And then, if it receives back hits, creates what's called a light merger underneath it, which sends another ray out to the light source to actually determine the color that should be drawn there. The other half of it, on the other hand, is the geometry manager. The geometry manager itself contains all the geometry and all of the data as a result, and then creates a bunch of intersectors. These intersectors are incredibly simple, and all they do is receive a ray in the form of a cast ray class, see if it intersects the geometry and determines where, and sends back to whoever sent it to them this option of intersect data. And that option of intersect data is either a none or a sum, and the none is no hit at all. A sum contains the information for whatever hit actually occurred. Now, these intersectors, we will create 8 to 16 or as many as we want, and we can route the rays being cast to the geometry to them in parallel and concurrently. And the specific methodology we used was a round-robin scheme. So, to actually make that easier to visualize, we have the Akka actor system itself containing everything, of which it has child actors in the image drawer and the geometry manager. The image drawer itself has pixel handlers, and potentially thousands of them, with each pixel handler being specific to one pixel. These pixel handlers, like I said, send rays to the geometry manager, and upon receiving back information, either create 1 or 0 light mergers, with a single light merger being created in order to send another ray out to see if it actually would hit the light source. Now, on the other side, like I said, we have the geometry managers, and the geometry managers have themselves these intersectors. We ended up specifically with either 8 or 16, but there are as many or as few as we could possibly want, and we specifically defined it based on the number of threads in the given machine it's being run on. However, this still isn't sufficient for distributed data. Because that geometry manager is totally monolithic in terms of actually containing the data, we need to find a way to create multiple geometry managers for different pieces of geometry. And so, that needs to be broken up by a parent actor, or basically a superclass, which decides which piece of geometry has which rays sent to it whenever rays are being cast. So we created the geometry organizer. The geometry organizer, we came up with 3 main schemes of how it would actually determine which geometry to send the rays to at any given time. And we simply called them the geometry organizer all, some, and few. The all is by far the simplest. All of these are going to break up the actual geometry itself into different managers, and the all, once it does that, anytime it receives a ray, just sends it to every single piece of geometry. After that, all it does is wait until all of those pieces of geometry return back all of their hits or no hits, and it picks the first hit sequentially, so the first hit time value hit, and then if it receives none, returns back none. If it hits any of them, picks that first hit and sends back that data. Incredibly simple. And it also can be incredibly fast if sending messages is very fast. Especially as well if single-threaded work is slow, because the actual work needed to be done in the geometry organizer is fairly trivial and fairly easy. The downside, though, is that you are sending out by far the most rays, and so if rays are expensive, it can slow it down considerably. The sum, on the other hand, has the actual bounds of each of those pieces of geometry, and so each of those geometry managers it knows the bounds of, and will send a given ray only to the geometries which has bounds that it intersects with. So if it would even potentially enter the total bounds of that geometry, will it send that ray? And so if there are several hundred rays that go completely off sides, it won't actually send that to any geometry at all and will instead just assume it's a none. As a result, without significant upgrade to the amount of single-threaded work on the geometry organizer, you get rid of, in many cases, half or more messages because the geometry won't tend to overlap super significantly. The most complex, on the other hand, is the few. The few actually, just like the sum, has the bounds of each of these pieces of geometry that the managers contain, and sends them to them in order. So it determines what was the first piece of geometry this would intersect, and only sends the ray to that piece of geometry, waits for the geometry manager to return it back, and based on that, if it's a hit, immediately short circuits and sends that back to whoever sent it to it, or if it didn't hit, sends it to the next piece of geometry in sequence. In doing so, it sends what should be potentially the fewest total number of messages possible. However, that is a significant amount of work being done on a single thread, and because actors only deal with messages one by one by one by one and lock, that single-threaded work is blocking and could be a significant bottleneck if single-threaded work is slow. Or if single-threaded work is slow and sending messages is fast. But on the other hand, if sending messages is slow, like potentially across a network, that could be a significant trade and upgrade. And again, to make that easier to see, we have the Akka actor system, and the image drawer side is completely the same. While on the side of the geometry organizer and the managers, it's a little bit more complex in that you have moved the geometry manager down one level and moved this new geometry organizer containing all of these geometry managers, but it's still more or less the same.
So in order to test our approach, we used a scene with a moonlet in the center and then about 8 million particles around it. And in order to make it sort of realistic, we have a white light on the right side of the scene to represent the sun, and a dimmer orangish yellow light on the left to represent Saturn shine. So you can see the two different colors in the visualization, this picture that we have right here. This picture is actually only about 10% of the entire number of rays and light and particles, in the entire data set, because our simulation, our scene is much more rectangular than this square, and so about 90% of our rays were sent off kind of into nowhere. So that is definitely something that kind of shows up when we are um, using our ray tracing stuff. We split up the steps into different segments to be able to view as much of the image as possible. So to test our timing, to test our approach, we did different timing results using bounding spheres and bounding boxes. And so we started off with our 8 million particles and tested it with the Akka sum, or all, sum, and few, so to see how many messages needed to be sent. And you can see the significant difference in bounding spheres between all and sum and few. And so there are significant differences between all and the other two. And then you can also see with bounding boxes that the same thing happens. There was also a bit of a difference between bounding spheres and bounding boxes, with bounding boxes being slightly faster, which is useful. And then we also wanted to see what the timing results would look like if we had a different viewpoint. So we would look along the x-axis above and in the plane, and tested it with bounding spheres and the Akka all, sum, and few messages. And so you can see those timing results in here as well.
So, conclusions and future work. So the conclusions are kind of interesting in that we saw a significant performance hit comparative to just base Scala or something like C++, but it was still more than tenable and more than useful. And the upside comparative to those methods is expansion of this code is incredibly simple to do and potentially could be done incredibly easily across a network or a cluster. As such, the most interesting next step would be to expand this code to Akka clustering and remoting. This clustering and remoting by default on Akka is pretty simple to do and should be pretty decent in terms of performance, because Akka really doesn't care where a message comes from or where it goes to, as these messages are of any type. And so as a result, sending them across a network shouldn't be a really difficult thing to do, and the way we've set it up, it should be incredibly easy to distribute those geometry managers, those pieces of data, across as many machines as we want and expand them fairly trivially.
Another potential direction for future work is including photometry and dust into our current approach. And so photometry sends rays from the light sources themselves, which is much more realistic, although it does use more resources in order to do that. It scatters the light and sees if the light intersects with the view plane. And so it can show the generality of our geometry work in that the geometry can be broken up and viewed with photometry as well as ray tracing. We also would like to implement dust and dust clouds into our current approach using photometry. So dust clouds are more easily done with photometry, and it's definitely different logic than distinct particles like we currently have. So dust is kind of like a cloud that the light goes through, and there's different densities and things like that that are very, very different than particles where the light bounces off.
So the other big issue that we have is that our code currently isn't resilient. Akka doesn't have any resiliency or self-healing features within it comparative to more traditional clustering methodologies. And so if one of those managers or one of those pieces of data goes down, you don't lose just the data. You also lose all of the rays that it was currently working on. So in the case of, say, a piece of data falling apart or downing, you can't really know with any really useful way which parts had been lost, both in the geometry, but also in which rays were lost as well. And so as a result of that, any time that any part of this cluster goes down, any part of this, even local cluster goes down, all of that ray tracing work is now completely moot, completely null and void, and is not accurate or useful. So it would be incredibly useful to add some sort of feature where the resiliency is improved or added really at all. Now, in addition, this code was initially actually put in for the summer conference and submitted there. And so as a result, it was actually submitted for late March. However, that didn't happen. On account of the COVID-19 pandemic, we were not allowed to go, and so we had to transfer this paper to the December conference. And we haven't been sitting on our laurels in that time. We've continued to work in the 6 or so months that have happened since the submission of this paper, and we've completed several of the things that we initially listed as future work. Most notably, we actually got an Akka cluster working, and that cluster was across 9 machines, and we could potentially make it as big or small as we wanted. And we actually got some data to compare with our sister project, which was working on doing a very similar kind of ray tracing, but instead using Spark. Spark being a more traditional Scala clustering. In addition, the photometry was also added as a front end and worked with a charm without any real hitches. Worked like a charm. And the only real addition that was necessary to be done to the back end, the geometry half of it, was that we had to add the ability for geometry to return their bounds, not only to the geometry organizer, but also to the front end section as well, and that was only really to prevent us from sending hundreds of thousands of rays completely wide of any geometry and only drawing useful things that might actually hit something. Work's not done though. There is still the dust to be added, because even though we added a photometry front end, it doesn't implement any dust or anything like that. And in addition, this code is still not resilient. The same issues will happen if one part of it goes down, as previously mentioned. So here is the GitHub repository that we've been working on and will continue to work on, with expansions coming to this project for as long as I'm willing to work on it, and potentially even after. In addition, here is a plot comparing our findings with those of the Spark teams. So the red plot is the all implementation of our code, with the blue and green being the some and few implementations as well. The cyan one, on the other hand, is their Spark implementation, and what you can see is that though the all is considerably slower than the Spark one for most of the plot, the some and few are actually considerably faster than the Spark version as the number of files increases. As a result of that, combined with the fact that Spark is actually considerably less memory efficient, this Akka implementation, due to its granularity of expansion as well as the ease of adding more and more parts to it, could be incredibly useful, even though Spark has advantages like increased resiliency compared to Akka. Now, finally, here are all references. Thank you so much for your time. My name is Kurt Hardee.
And I'm Elizabeth Ruetschle.